Hey everyone, and welcome to this explainer. Today we're diving into the totally fascinating physics of why light just doesn't travel forever. And, to really do this topic justice, we're going to tackle this by presenting our findings in a structured research paper format. It's honestly the perfect way to break down a concept that feels incredibly intuitive right up until the exact moment the laws of astrophysics tell you otherwise. So, get comfortable and let's dissect the actual mechanics of light dissipation.
Setting our roadmap for today, we're going to progress right through an abstract, background, theorem, analysis, and then wrap it all up with a discussion. We'll basically be moving logically from weird terrestrial anomalies right here on Earth, stepping through the mathematical mechanics, and then scaling all the way up to the massive implications for interstellar communication.
All right, part one, our abstract, the searchlight anomaly. Let's jump right into isolating the core discrepancy between what pop culture tells us and what actual physics dictates.
There is just this wild, stark contrast between our expectations and reality here. I mean, think about it. Whenever you watch a sci-fi movie, lasers and energy beams just shoot endlessly through the vacuum of space, right? They maintain this uniform, perfectly consistent brightness, just solid, unyielding lines of glowing energy. But then, think about physical reality. If you've ever been to a big event, like a movie premiere, and you see those massive terrestrial searchlights shining up into the sky, you know exactly what actually happens. You get this brilliant, intense beam shooting up from the ground, but then it just kind of visibly fades out. It literally looks like it completely stops right in the middle of the dark night sky. So why does it do that? If light travels forever in a vacuum, where on Earth does the energy from that massive bulb actually go?
Moving on to part two, our background on the mechanics of visibility. To really grasp the foundation of this whole anomaly, we need to break down a pretty famous analogy used by astrophysicist Neil deGrasse Tyson.
So, to understand the particle physics of light, we can use what Dr. Tyson calls the butter gun experiment, which is exactly what it sounds like. Imagine you have a highly specialized gun, and it fires a perfectly consistent, specific amount of butter. Let's say exactly 1 tablespoon. If you fire that at a piece of toast right in front of you, you get a nice, thick layer of butter covering that specific little square. But if you move the toast all the way across the room and fire again, that exact same tablespoon of butter now has to spread over a way wider area to reach the target. Step 3 is just the natural conclusion of this geometry. As you keep moving that target further and further away, that original finite amount of butter becomes infinitely thin. It didn't disappear from existence, right? It's just stretched across an impossibly large surface area.
And that brings us to the crucial point here. Light particles, or photons, behave identically to that spreading butter. A searchlight on the ground is basically firing a specific, finite amount of energetic photons into the sky. As those photons travel away from their source, they naturally expand outward. They don't die off. They don't run out of gas or hit some invisible wall in the atmosphere. They just lose their concentrated intensity, constantly spreading and thinning out over incredibly vast distances.
Okay, part three, the theorem, the inverse square law. We've got the butter analogy down, so now we really need to lock in the strict mathematical framework governing all this dissipation. Let's look at the hard physics.
What we're dealing with here is the formal definition of the inverse square law. This is the fundamental physical rule that completely proves why light beams just cannot maintain uniform intensity. It states that the intensity of a light beam is inversely proportional to the square of the distance from its source. Now, I know that sounds a bit dense academically, but it essentially just means that light's brightness drops off at a brutally fast mathematical rate the further it moves away from the bulb.
What's absolutely fascinating here is the sheer severity of this math. Just look at how rapidly that intensity drops. Let's say you're standing 1 mile away from a searchlight. It has a certain brightness. If you simply step back and double your distance to 2 miles, the brightness doesn't just neatly drop by half. No, it precipitously plummets to exactly 1/4 of its original strength. Step back to triple the distance, it drops to 1/9. At 4 times the distance, you're at 1/16. It is a rapid, exponential plummet in intensity that practically swallows the light whole. Which brings us to part 4, our analysis, the column perspective. We have to evaluate the atmospheric mechanics of why a searchlight even looks like a solid column from the ground in the first place. Because, think about it, if light just spreads out like butter, why does it look like a solid tube?
So, let's break down this visual illusion step by step. First off, just a basic rule of human biology. We only see light when photons physically and directly enter our retinas. So if a searchlight is pointing straight up into space, totally away from you, why can you even see it from miles away when you're standing off to the side? Well, it relies entirely on a process called atmospheric scattering. You see, our atmosphere is far from empty. It's totally full of dust, smog, and moisture. As that concentrated beam shoots up, photons hit those atmospheric particles, ricochet sideways, and travel directly into your eye. But tying it back to the inverse square law and our butter gun, as that beam travels higher and higher, it aggressively thins out. There are drastically fewer photons available per square inch to actually hit those dust particles. And eventually, the scattering just drops completely below the threshold of human visibility. The crazy part? The light hasn't actually stopped. It's simply thinned out so incredibly much that there aren't enough sideways ricochets left to trigger your optic nerve. The beam is still going, your eyes just can't detect it anymore.
Finally, let's jump into Part 5, our discussion on alien interception. Let's scale this physics up to the size of the cosmos and see how this builds into literally one of the most fascinating topics in modern astronomy.
This leads us to a massive, incredibly practical question when it comes to the search for extraterrestrial intelligence. Humanity broadcasts radio waves and light into the cosmos constantly. But if a massive, high-powered terrestrial searchlight fades out to the human eye after just a few miles because of spreading photons, are our signals even reaching distant alien civilizations?
Well, the answer, which is governed strictly by the mathematics we just analyzed, is pretty humbling. Because of the inverse square law, everyday light and radio waves leaving Earth lose their intensity with aggressive exponential speed. By the time our television broadcasts, our radar pings, or even our stray city lights cross the vast, unfathomable oceans of interstellar space, they've spread so incredibly thin, they effectively become completely indistinguishable from the ambient background radiation of space itself. Without an unbelievably focused, impossibly powerful directional beam, our planetary footprint just dissipates into the cosmic static long before it ever reaches a distant star system.
So I want to leave you with this final humbling thought to ponder regarding the silent mechanics of our universe. Because remember, the inverse square law works both ways. Just as our light thins into absolute nothingness before reaching them, their light does the exact same thing before reaching us. Seriously, how much invisible, infinitely thinned out light from distant ancient civilizations has already washed right over our planet without our greatest instruments even noticing?
It's kind of wild to think about.
I really hope this explainer completely changes how you look at the stars tonight.
Thanks so much for joining me for this analysis.